speaker is Fruchter from Bonn, and he's going to talk about virtual homological torsion and profinite rigidity works.
Thank you for the introduction, and thank you for the organizers for the opportunity to speak. So this is a joint project with Dario Ascari, and before I start, I should say that this project is more of a topological statement about certain two complexes rather than like a straightforward profinite type of project. And the plan for today is to go maybe reverse the order of the title, start a bit with the question of profinite rigidity of words. So I plan to motivate this question, explain a bit why it's hard and tell you what is known. And then I will talk about how the topology of certain two complexes can help us tackle or at least give a small contribution toward this big open problem. So the idea of the question of profinite rigidity of words is to ask the following. So suppose we are given a word in a free group, just an element in a free group, and we want to see how it behaves in different finite groups, and try to deduce from that what can we say about the world. To what extent does its behavior in finite groups determine it? And maybe to motivate things, I will go a bit back in time and start with a very old problem. So yeah, maybe go more than just a bit back in time. So that's a question of Diophantus of Alexandria. From 1750 years ago. And the problem says the following. And so I will start by phrasing it the way he did, and then I will rephrase it in modern terms that is a bit more suggestive as to what we want to do with this question. So he said, find 4 squares that sum to a given number. And I think it's still debatable whether he meant like just find some 4 squares that sum to some given number. He also didn't know what a 0 is at the time. But some people like to think that, yeah, he meant what we think this means. Or in other words, given the following polynomial, is the evaluation map which takes 4 numbers, plugs them into the polynomial, and returns another value, surjective. So I'm sure that probably everyone in the room have heard about this problem, which is more famously known as Lagrange's 4 square theorem. From 1770. And I should also say that this was later generalized in the early 20th century by Hilbert to powers that are greater than 2. So there we might need to take a sum of more than just 4 powers, but these maps are always surjective.
Excuse me? Does n contain 0?
Yes. Okay, so some of us are very much algebraists, but some of us care just about groups. And in groups, we don't have the luxury of taking products and sums. We have a single operation, and not everything is commutative. So we might want to ask similar questions, again, in the vein of taking some kind of a form, plug values into it, and see what we get. And this is indeed another famous conjecture, this time of Ori, from 1951. And he asked the following thing. So he asked, is every element of every finite simple non-abelian group a commutator. And again, to make this a bit more similar to the phrasing of Diophantus's problem, we can ask the following. So given the commutator word in the free group on two elements, is the word map on every finite, simple, non-abelian group surjective. And what I mean by a word map is, again, we are going to treat this free group element just as a form into which we can plug other group elements, which will give us a map from the direct product of two copies of G back to G, which takes a pair of elements, G and H, and maps them to the value, to the W value that corresponds to them. So in this case, just the commutator. And just like Diophantus's problem, this has also been solved since. This time it didn't take 1700 years. And so this is now a theorem of Liebeck, O'Brien, Shalev, and Thiel.
Yeah, but also the classification of finite simple groups. Right?
Of course, of
It
course.
wasn't available when we were asked the question.
Yes. And I should also say that a subset of these authors and also Larsen started studying this problem for other words, which are not the commutator, and they reached a very similar conclusion. So it might not be that every word induces a surjection on every finite simple group. For example, if you take the square of a primitive element, it won't induce a surjection. But they did show that every element in a finite simple non-abelian group is the product of two W values for every word W. So maybe this suggests that if we want to study how a word behaves based on how the word maps behave on finite groups, just looking at the image of the word map, maybe it's two cores of an invariant.
Sorry, that
and it's
last
not
statement about arbitrary words has to admit finitely many exceptions.
Yeah, so as long as the finite simple group is big enough, then we do get, that every element is the product of two W values for every W. Okay, so this suggests that maybe just looking at the image of word maps is two cores of an invariant. And we might want to ask ourselves, what if we take an element and we count in how many ways can we get it as a W value? So for this I will define the following thing. So suppose we have a word in a free group. So this word induces a word measure which I will denote by PWG on every finite group G. And the way this measure is defined, like I said, is just pick an element of G and check how many tuples give this as a W value. So, yeah, given any finite subset of G, any subset of G, we define the measure of it to be the number of tuples in G to the n whose W value lands in A divided by the total number of tuples. And again, a good example to have here, perhaps the simplest example, is when W is a primitive element, in which case the world map is a projection, and the corresponding world measure is always uniform on every group G. So this gives us a final invariant to look at, but other deep works of Larsen, Shalem, and Thiel tell us that maybe this invariant, it's not necessarily very good at differentiating words. And what they proved is that, I won't go into detail, but for many words, the word measures that they induce on finite simple groups tend to uniform in the L1 norm as the size of the finite group goes to infinity. So I hope that with this you're convinced that telling words apart by the measures that they induce on finite groups is a difficult problem. And the next thing that I want to do is to relate this question to other things that we talked about this week, and in particular to free profinite groups. So there is a very nice observation that I believe was known to experts, but the first place where I saw it written was in a paper of Liam Hanani and Miriam Fruchter. Which says the following. So given two words in Fn, these two words induce the same measure on every finite group, if and only if there exists an automorphism of the profinite free group that takes one to the other. And with this, we define the following notion. So maybe instead of trying to attack this problem as a whole and showing that every word is determined by these word measures, maybe it makes sense, because it's a hard problem, to do it case by case. And they call a word W profinitely rigid if for any other word if there is an automorphism of the free profinite group that takes W to W prime, then there exists an automorphism of the free group taking W to W prime. So you can also think of it as a case-by-case question of the question of profinite homogeneity that Gianluca mentioned yesterday. So yeah, as you probably understand by now, people believe that every word should be determined by the word measures that it induces, or alternatively that whenever two words lie in the same profinite automorphic orbit of the free group, they lie in the same orbit. And so the conjecture, which I know was stated by Alex, it was stated by Shalev, and by other people, including Simon Andre and Gianluca, is that every free group element is profinitely rigid. And just like the question of profinite rigidity, where we don't have many examples of groups that are profinitely rigid, the situation is pretty similar with this question. We don't have many examples of words that are profinitely rigid. Maybe because less people have been thinking about this problem, but I like to believe that it's also because this problem is pretty hard. So what do we know so far? So before I list the overwhelmingly small list of known examples, I should mention that by works of Alex and Hanani May and Pudel, we know that if W is profinitely rigid, then so is every power of W. So I will only be talking about words that are known powers. I might not always be saying this, but I always mean this. And the list of examples of words that are known to be profinitely rigid is the following. So first, and perhaps most famously, are primitive words. Or in other words, if a free-group element induces the uniform measure on every finite group, must it be primitive? And the answer is yes. This is the theorem of Bartniczewski and Pudel in 2015. And it also follows from Wilton's theorem that was mentioned in more than one talk this week. And it also follows from the work of Andrei and Alejandra. That had to do with the detection of three factors of finite conditions. Another case that we know is when W is the commutator of two primitive elements, and this is by Hanani Meir and Pudel. And another known case also follows from Wilton's theorem, and that is that surface words are profinitely rigid, and what I mean by that is exactly the words that are the relation of the surface world. So words in the automorphic orbit of the product of all commutators of basis elements in a free group of even rank, or the product of all squares in a free group. And finally, the profinite corollary that I would like to mention today that follows from the topological statement that I will mention later is the following. So partial surface words are also profinitely rigid. And what I mean by partial surface words is to take any of these words and truncate it. So either a word of the form, the product of commutators of some basis elements, but here the rank of the free group doesn't have necessarily to match this, so we leave some extra room in the free group, or the product of squares, again inside a bigger free group. And I should also say that this also follows from the results of Andrei, Pavel, and Enrique that were mentioned earlier this week. And I think that every profinite corollary that I will mention today also follows from their work.
These are always elements of the same basis, three bases.
Um,
You say they are primitive, you actually mean that they are, the subset of them is contained in a single free basis.
yes, Yes, exactly. So I will get to it, but what I mean here is that if you take this as a relation in one related group, you will get the free product of a free and a surface group. So yeah, they all have to be co-primitive. The elements in here and in here.
The same thing too.
Yeah, and the same applies for surface walls. And here. So in some way you can look at this as somehow like gapping, you know, like bridging a little gap between these two things. So we know it for the commutator, we know it for the square of a primitive world, and we know it for the product of all squares of primitives or the product of all commutator primitives, and this somehow bridges this gap. Okay, so what I want to do now is to relate this problem to the problem of profinite rigidity in the class of hyperbolic graphs of free groups with cyclic edges, which perhaps in this room it's mostly famous as the best class in which we can do a Maslenikov. But I think that in the GGT community it's more famous for just being a very convenient class of groups to test new things. And also many things that happen there go hand in hand with things that happen in the world of three manifolds. So maybe the most famous examples are subgroup separability and specialness. And for this we observe the following. So given a word in a free group, we denote by dw the double over this word. And what I mean by that is we take two copies of the free group and we identify the copies of W in each side. Now it's not hard to see that if W and W prime lie in the same profinite automorphic orbit, then the corresponding profinite doubles are isomorphic. But these are just the profinite completions of the usual doubles. And this means that solving this question for a given W is the same as profinitely distinguishing the corresponding double from any other double. And another thing to know, is the following. So a word W is a partial surface word. If and only if the corresponding double is isomorphic to the free product of a free group and the surface group. So somehow our task, in order to show that these partial surface groups are profinitely rigid, our task is now reduced to showing that free products of free and surface groups are profinitely rigid in the class of doubles, or more generally in the class of hyperbolic graphs of free groups with cyclic edges. And this is something that follows from the main result in this project. And somehow, yeah, the main motivation for this project, I guess, is the homology torsion growth conjecture that was mentioned by both E and by Holger. But somehow, yeah, in this case, it also gives us this nice small profinite corollary. So what we prove is the following. So suppose that G is a hyperbolic graph of free groups with cyclic edges. such that G is not isomorphic to the free product of free and surface groups. So if this is the case, what we show is that we can always find virtual homological torsion. And not just that, we can find any virtual homological torsion that we want. So given any finite abelian group M, there exists a finite index subgroup, Gm of G, such that the abelianization of Gm has M as a direct factor. And an immediate corollary of that, using the Wilson-Zaletsky machinery of, and also Garrett Wilks of profinite point graduality groups acting on profinite trees, we get that free products of free surface groups are profinitely rigid among hyperbolic graphs of free groups with Z edges. So before I tell you about the proof, I will say while this result is very far from showing that these groups admit positive exponential torsion growth in homology, it does match the state of the art of what we know in the world of three manifolds. So Hongbin San proved essentially the same thing for closed hyperbolic three manifolds. And the idea behind this proof is the following. So given some three manifold using the Kahn-Markovich construction, he was able to immerse a certain two complex into M, which looks like this. So it looks like a surface with boundary, where the boundary of the surface goes p times around the loop. So this loop exactly gives us homological torsion in xp, and then xp is immersed into M, and using a virtual reduction, immerse the homology of xp as a direct factor in the homology of a finite cover of M. So our tactic is pretty similar. Our goal is to take a two complex whose fundamental group is G and immerse another two complex that has the homology that we want into that two complex, and then use a virtual reduction to push that into the homology of a finite index subgroup. So our goal is the following. So we will set G to be the fundamental group of the 2 complex. And here this 2 complex is just a collection of graphs glued together by cylinders. And what we need to do, given M, we want to find another 2 complex whose first homology contains M as a direct factor, and then we want to immerse Ym into X and finish it off with a virtual attraction. So I think I will start by telling you a bit about what are the 2 complexes Ym that we take.
What is M? H1 of Ym is equal to M?
So M is a finite abelian group. And I want to have this as part of the first homology.
It's
of
not
the
a
complex.
manifold anymore.
No. It's now, it's a finite abelian group. Do this. So the first step, we are going to start with M, which by the structure of finitely generated abelian groups just looks like this. So it's a free abelian group where we apply some constraints of the form some power of some generator vanishes. And we are going to convert that into a system of equations that looks a bit differently. And the equations that we use are ones that look just like the sum of basis elements vanishes. And after we do this conversion, now this form of equations gives rise to a very natural geometric realization of this group as the homology of a 2 complex. And so what we are going to do is we are going to associate to each equation we will associate the surface with boundary. And each variable will correspond to a boundary component of that surface. And then the system of equations, by looking at which variables appear in which equations, tell us how to glue these surfaces together and get a 2 complex with this first homology. And so I think maybe it's better explained with an example. And these complexes, Ym, tend to become very big and very complicated very quickly. So maybe I will do the simplest possible example and just go with M being Z mod 2. So for Z mod 2, which is just Z, the single equation, 2x equals 0, we convert it into something of the following form. So we take a bigger free abelian group and choose 4 generators of our choice. Let's say x1, x2, x3, and x4. And the collection of constraints that we now pose on this free abelian group is just xi plus xj, whenever I smaller than j. And what this gives us is the following complex. So like we said, each variable corresponds to a boundary equation of a surface, to a boundary component of a surface, and each equation corresponds to a surface. So we get 4 of these boundary components. And each equation gives us a surface that bounds exactly 2 of these. For this y z mod 2, we indeed get that the first homology is z mod 2 plus some free abelian group. Okay, so now we have a good candidate of a type of complex that we want to immerse into X. And this is where the real work actually begins, and where we need to use Wilton's theorem that I mentioned, and that was stated here this week. But I will state it in a slightly different form. So yeah, I think Andre stated it as a purely algebraic statement about profinite projective groups, and I will state it in the form that Henry stated it originally. So suppose we have G hyperbolic enough free groups with Z edges, then if G is not free, then there is a surface that immerses into G.
So can I ask a quick question? So hyperbolic here means the group is hyperbolic.
Yes, so okay, to prove our theorem, we need to go a bit deeper into Wilton's machinery, and maybe I will make the following remark. So in Wilton's theorem, the assumption that G is not free is used as a lower complexity bound so we get a lower bound on the complexity of vertex links in the corresponding 2 complex. And these complicated links actually allow Henry to build it like surfaces with boundary, whose boundary agrees with the edge groups of the original graph of groups, and kind of embed the surface into G piece by piece. Now, our assumption, now we have a stronger assumption, so we don't just assume that G is not a free group, we assume that it is not the free product of free and surface groups. So this gives us a sharper lower bound on the complexity of G. And the complexity of G can manifest itself in one of two ways. One way gives a very easy way to embed Ym into G, and the other one, that's where most of the work goes. So either the underlying graph of G is complicated, and here, yeah, the underlying graph of G might not look complicated, but maybe when we pass to when we refine it into a JSJ decomposition, we can see this complexity. And what I mean by complicated here is that there are three edge groups that are identified together, which gives us this branching behavior that we can see in each of these boundaries, where three different surfaces meet together. And so this gives us, straight away using Wilson's theorem, an immersion of Ym into X. Or if the underlying graph of G is very simple, which is something that can arise, for example, when G is the double along a complicated word. So in which case, all of the complexity of G is centered around this attaching map and not in the configuration of the underlying graph. So, or for example, when G is the double along a complicated word, and here by complicated, I mean, for example, when W is rigid, which means that each vertex group, so each free group on each side of the double, doesn't have a cyclic splitting relative to W, and in which case this double is the genuine JSJ decomposition of G. So in this case, we get that there is a vertex of X, whose link is even more complicated. And this complicated link gives us a bit more of a wiggle room to construct something a bit more elaborate around this link. And what we get from this is that we construct something that we call artificial branching. Around V. So this artificial branching kind of replaces what we see here in this picture, where we have many surfaces coming together. But constructing this artificial branching is not enough. It doesn't allow us to immerse Ym into X, and we do need to work a bit harder. So what we get in this case is the following. So we have Ym, and we have X, and instead of immersing Ym into X, we need to do something that is a bit like folding a graph and only then immersing it. So we get here a quotient map into a different 2 complex that immerses into X. And now this Y prime M puts us in a good position to try and inject homological torsion into X. The problem is that it's hard to ensure that this quotient map induces an injection, at least on the torsion part of homology, which is what we want to preserve going from here to here. And what we use here, so in order to show that this map is injective, at least on the torsion part of homology, we use Caligari's rationality theorem. For stable commutator length. So this theorem essentially says that stable commutator length in a free group is always rational, but it also has an equivalent formulation in terms of surfaces bounding certain elements that land in the commutator group of a free group. And this allows us to show that if there is something that dies in this quotient, then whatever dies must bound the surface, and it actually lets us improve whatever we use to construct the artificial branching piece and improve our situation until we reach a state where things can't die anymore and we get this immersion. Yeah, and to be honest, I only planned for 50 minutes. I thought that in all talk there would be 10 minutes for questions as usual, but it seems not to be the case this week. But yeah, I will leave you room to ask questions and maybe have lunch early.
Do you explicitly solve some linear programming problem at some point, or is it hidden in Caligari's theorem?
So it is hidden in Caligari. So we use it to have some kind of a minimality argument, but we don't have the whole, the whole strategy of having maybe some map that improves your status and have some like miracle that tells you that there is a solution. So we hide this into Caligari and it lets us run this minimality argument, which shows why the improving thing should stop. Yeah.
In this whole construction, can you somehow control how deep into the index you need to dive to exhibit a certain M?
So if the hyperbolic graph of free group that you start with already just has somehow like surface pieces, so if it's just J decomposition doesn't have a rigid piece, then it's very easy to do. Otherwise, we can't control the index, but what we do know how to show is to find an exhausting sequence of finite index non-normal subgroups that exhibits exponential torsion growth. So I think that this is something that you did this for 3 manifolds, giving up normality and getting positive exponential torsion growth. By embedding many projective planes, so this is something that we can do. Normality obviously is a lot harder. I have some reasons to believe that just this object should have exponential torsion growth in normal subgroups, but I don't know how to do it yet.
So when your group G has torsion, do you have to take extra care of this?
So G is always torsion free as the graph of free groups with Z edges. So the same holds for a graph of virtually free groups with virtually Z edges, but then the same thing holds as long as you are not virtually the free product of free and surface groups.
So as we discussed yesterday, we can define this problem, of bringing down the atom with infinitely defined. Do you know an example of one that is profinitely rigid, but it does not satisfy this assumption? Because the only example I know, this counterexample that I mentioned yesterday, is not profinite. It fails this, but it's not profinitely rigid.
So you mean a group that is profinitely rigid, but it's not profinitely homogeneous?
Homogeneous or whatever we want.
I don't know an example. So I know like simple examples of these profinitely homogeneous groups, like 3 abelian groups, for example. I think it's very easy to show.
Yeah, also with my methods.
Yes.
Sure,
but I don't know an example. I don't know an example. No.
So in my paper, I give one it's a billion by 5, but it's not profinite. So we don't even know at all. Yeah.
I think in general this question, so it hasn't been studied much for groups other than a free group. I know that Pavel has a result about simple closed curves on the surface when they are connected by a profinite automorphism. Then if one is a simple closed curve, then the other element of the surface group also has to be a simple closed curve. And so I think that this is the only result that I know about this question, about like retrieving group elements from the way they behave in the profinite completion, not for a free group. This is the only result that I know.
Just a kind of an historical remark. At least in the old days, when I was interested in that, I was usually thought about it simply in the language that automorphic classes in the free group are closed in the profinite topology. And the reason I was interested was because this would give a proof to Whitehead theorem that the question whether two elements are decidable or not is whether two elements are equivalent under automorphism or not is decidable, because if this would be kind of a natural continuation to the fact that, you know, if a group is residually finite, then the whole problem is decidable. If group is conjugacy separable, then the conjugation problem. If it's automorphic closed, then then this Whitehead theorem will be proved. Okay, so far it didn't work. Just been listening to you, and now I see that you have a lot of topological intuition, which I don't. Maybe it's worthwhile to go back to the Whitehead theorem, which I never really understood well, and try to look if you can go backwards. Maybe there is already there, because you see, Whitehead theorem really has such topological ideas in its background.
Yeah, maybe I tried to do something maybe a bit similar but a bit different. So instead of going for Whitehead's algorithm, I went with Doron's algorithm from his thesis. So he has a different algorithm that checks the same.
For the primitive or for all?
So no, just checking if something is primitive, and I thought maybe I could try and translate this into a homological condition, and maybe I could gain more insight, and maybe also for different kinds of elements, but somehow like recovering is he calls it the lattice something, some kind of an analysis lattice of what happens. But I didn't see an obvious way to translate it into homological condition.
Well, Alex made his historical remark. I want to do also terminological remark. There is a parallel terminology is developing. So there is notion of twisted conjugacy separability. And so, for example, this conjecture that is Lyubotsky, Shalev, etc., can be formulated in this term like whether Fn is twisted conjugacy separate. So maybe one has to look at this and develop somewhat unique terminology for not confusing people.
Okay, I will look into that. Thank you.
Sorry, so when you get the corollary about partial surface words, how do you, are these doubles always hyperbolic? How do you apply the theorem?
So yeah, if you have a partial surface word, the double is always the free product of a free and a surface group.
Yeah.
So they fall exactly into the kind of thing that we can differentiate from other graphs of free groups using this homological torsion.
Yeah, but what about the hyperbolic hypothesis? Is what I was asking.
So a free product of a free and a surface group is always hyperbolic, and in general the double, as long as the word is not a power, and
okay.
the double is always hyperbolic. And if the word is a power, then it's also easy to tell this case apart.
There are no more questions. Let's thank the speaker again.